Hello AP Physics C students, get your notes open. It's time to start doing some new material. Now the great thing is I found a PowerPoint presentation online that would have gone through a lot of the stuff that I would have done myself, and so I type a lot less and I don't have to worry about formatting everything. I still have some things that I do, but this is going to make things a lot easier. Okay, so this topic is about inductance, or what this PowerPoint calls self-inductance. Read this slide, I'll go through a couple things, and we'll go step by step and take notes as appropriate wherever you think it's good to do some stuff, definitions, diagrams, things like that. Okay, so here we have just a basic circuit here. Battery, resistor, switch is open, no current flows. Close the switch, all of a sudden charges start flowing through here, and because charges are flowing around in a loop, you can use your right-hand rule shortcut to show that the magnetic field produced by this loop of wire, which is just one loop of wire, points out of the page. Nothing fancy here. Read, pause, come back when you're ready. Okay, so watch what happened, right? There used to be no field because of this circuit was open. All of a sudden you close the circuit, all of a sudden a field appears because of that, which is pointing out of the page, but remember, Lenz's law says the universe doesn't like that. So if all of a sudden you put a field out of the page, the universe says, well, we want to get rid of that field. It's going to induce a field within the confines of this that points into the page. That's what we're calling B induced here, the blue X's, which means that it's going to try to force charge around the other way, right? With your right-hand rule shortcut, show that a field pointing into the page would have charges flowing the other direction, as if there's a sort of like phantom battery over here forcing charge the other way. This is what we call a back EMF. It's opposing the actual EMF of the battery, sort of trying to back up against it. It's not really there, but it's as if there is a battery trying to force charge the other way, trying to remove the field that all of a sudden you put there. Okay, so this is saying, why don't you notice this happening? Well, that's probably because there's only one loop of wire, but if we have a whole bunch of wires looped around together, then there's going to be a very measurable effect here. There's going to be a delay in the current reaching its maximum value, the value we're used to seeing. We don't normally see this in the lab because we only have one loop of wire. When we loop the wires all around together, now we call it an inductor, which really is just the same thing as a solenoid, right? We've seen this before in class. The wires looped around many, many times, and so that enlarges the effect, and we'll see a very measurable change in the current over time. Okay, so they're calling this back EMF, E sub L. Remember, this is the capital E. That really should be a capital script E. That's the way we write it. So if you're taking notes here, you write this as a capital script E. That's our EMF symbol. And it's again called this back EMF idea, that it's sort of this phantom source of voltage that's opposing the actual source of voltage, trying to remove the magnetic field, and it sort of, it lessens the current for a certain amount of time. So we're going to find this new term, capital L, called the self-inductance, or we're just going to call inductance. And I'm going to derive the equation. So at this point, if you haven't really been taking notes about this, or maybe hopefully you're writing some of these definitions here, we're definitely taking some notes. So we're going to start with Faraday's law, negative N d phi dt. Phi, remember, is BA cosine theta. What is changing? Well, because the current is changing through the loop, it's the magnetic field through the loop is changing. The area doesn't change, the orientation doesn't change. We have a dB dt. Since we're calling an inductor, which has inductance L, basically a solenoid, we want to remind ourselves the magnetic field of a solenoid is mu naught Ni. It's our permeability of free space. And so we're going to take the time rate of change of magnetic field from the solenoid. So dB dt, mu naught is a constant, N is a constant. It's really the current that is changing. So it's a di dt. Now here's where it gets a little bit weird, but follow along here. I'm going to multiply top and bottom by the current. All I do is multiply top and bottom by current. Why am I doing that? Well, on the top here we have mu naught Ni, which is the magnetic field produced by the solenoid. So I'm going to write this as B over I di dt. And you may start to worry, oh my gosh, there's going to be another separation of variables, take the integral, the natural log. No, it's actually not. I know it looks like it's setting up for that, but just watch what happens here. So here we're saying dB dt is B over I di dt. So we're going to take all this and substitute it right in here for dB dt. There's dB dt. I put in parentheses here, V over I di dt. Why am I doing that? Well, I'm just going to rearrange the variables again, taking the b to the outside, which is the constant. So now it's n times BA cosine theta over I di dt. Why am I doing that? Well, BA cosine theta, what's that? That's phi. So watch what happens, right? Where there's n loops of the wire. So I'm going to replace nBA cosine theta with phi, and now we have negative phi m over I di dt. This term here is what we're going to call the inductance, capital L, where we define L as flux over current. This is our new term, which we're calling inductance. We're going to box both these in as new equations. And here we'll define capital L as inductance. We'll talk about what inductance is soon. The PowerPoint will describe it. This is a scalar quantity. The units come from the equation. Remember phi here, flux is in Webers. This is Webers per amps, which we redefine as the Henry, capital H, after Mr. Henry. So we just go back here. This looks an awful lot like Faraday's law. So this is what we're calling Faraday's law for this induced EMF, this back EMF, because there's a changing current, a change in magnetic field. Okay, just read this slide, pause it, absorb the information. So you can see here that when they compare this to Ohm's law, they're saying that the inductance, this capital L, is playing a similar role to resistance. Resistance opposes current, right? It limits current. This is opposing the change in current. When current is changing, we have this similar sort of idea that somehow opposes the change. Go ahead and read. Here I'm trying to draw the circuit diagram, the schematic version of the solenoid or the inductor, basically just a bunch of wires looped around together. Read. So you can see the inductor is playing a role of storing energy, except instead of storing energy in an electric field, like the capacitor stores energy in a magnetic field. We'll get to that soon. Okay, these next couple slides go through a theoretical way of describing this EMF. I want you to just, pause the video. Read through these things. I'm not gonna narrate it. Just read through, so you can see how they figure out how this relates to other electric fields and how we can apply Kirchhoff's rules. I'm going to quickly with clicking. Certainly pause the video so you can read at your own pace. I just realized that there's a little bit of extra bit of an arrow there. Just disregard that. I was trying to. The original PowerPoint didn't have arrowheads on these, so I was putting them on. So just disregard that. Okay, here's where it starts to get really important. Hopefully you were pausing the video and trying to absorb this information as we went. So here we're talking about this idea of we have this changing current, which means we're going to have a potential difference across the inductor. Here's our inductor, or the solenoid here, right? And so here, when the current is increasing, this is going to be a positive number. We're going to have a positive difference from A to B. This is going to be at the high potential, this is going to be at the low potential. Because the current is increasing, there's a positive number. So delta VL then is negative. Why are we saying delta VL is negative? Well, because when we do delta VL, the potential difference, we do VB minus VA. This is written as VA minus VB, right? This is at the high potential, this is a low potential, so going this way, we're going down in potential. That is a potential drop, a voltage drop across this inductor when the current is increasing. Here's another way to look at it from the perspective of Faraday's law and Lenz's law. Where once again, this is the positive end, this is the negative end. We're going across this way, so it should be a decrease in potential. They've written it the other way, though. Remember, we go this way, so this would be a negative potential difference. So here they're just going through the three situations. If current is increasing, there's a positive number because the IDT is positive. Current is decreasing, there's a negative number because the IDT is negative. This is also important. Once the current levels out, there's no change here, so there's no difference in potential. So at that point, what happens? Well, the solenoid or the inductor kind of just acts like a wire. There's no potential difference across. It's an ideal wire with no resistance. So once the current evens out, there's no voltage across the inductor. Okay, so now we go with our usual way of thinking about it. When we do a potential difference, we do final minus initial. So VB minus VA, so all those signs we were learning before switch. So this is, I think, the more useful version of what we're doing here, right? So if current is increasing, the IDT is positive, and since there's this negative sign in the equation itself, this will be a negative voltage. This will be a voltage drop across here when current's increasing. When current is decreasing, well, the IDT itself is negative. This negative sign here means that this is going to be a positive. There's going to be a gain of potential across it. And of course, when this is 0, well then the voltage across the inductor is 0 as well. So this slide here is really, really important for understanding the signs that go along with this. Alright, so now we're going to put it in conjunction with a resistor. Here's where it gets fun. So read this. We're going to do Kirchhoff's loop rule for the current increasing, right? We close the switch, all of a sudden there was no current, all of a sudden there is a current, the current is increasing. What happens? Well, we start by writing all the voltages. Now here I'm not putting the proper signs on them, I'm just saying there's going to be a voltage across the battery, there's going to be a voltage across the resistor, there's going to be a voltage across the inductor, and they all have to sum up to 0. Now we're going to put the proper signs on them. So as we go this way, there's a gain of voltage across the battery given by EMF. We go through the resistor, which is always going to drop. We're going the right way through the resistor, so we're losing IR. Here we're using lowercase I for the time-dependent current. And since the current's increasing, we're losing voltage across the inductor. We're solved for dIdt. And separate the terms here. Alright, so here they're going through the boundary conditions. When time equals 0, there's no current flowing, so little I is 0. And so dIdt equals EMF over L. The time rate change of current is just EMF over L. That's the boundary condition when time equals 0. What happens after a long time? Well, the current reaches a constant value, so the time rate of change is 0. dIdt is going to be equal to 0. Set that equals 0. Set these two equal to each other. And we see that the current, after a long time, is just our usual EMF over R. So almost again as if this just becomes a wire offering no resistance, no change to what's happening here. If everything is normal, it's a steady state. Okay, so here's where it gets interesting. What happens in between? So we start with this. We're going to just rearrange a little bit. We're going to divide everything through by R. So at this point, I want you to pause the video and see if you can take some more steps here to start to solve this, to solve for a function of I with respect to time. Every once in a while, I'll do some stuff along the video, so if you get stuck, unpause the video, see what I do. We do our usual separation variables, and I don't really like this step here. I think I would have gone directly from this step to this step over here, but it's just a matter of how you do that. We want to do our usual separation of variables, right? Current and current, everything else on the other side, just like we've done for an RC circuit. At this point, you may want to do a U substitution if this is bothering you here. So U equals I minus EMF over R. Take the time derivative of this, and we get to U equals dI, so you can do U substitution. So at this point, pause the video and go on from there. Okay, here we do our usual integral. I take this extra step that the PowerPoint doesn't. Right, we do our usual natural log, where this is our U. If you had done that, then you go back and substitute U back in. Here we go. This is what we should be getting. What does the graph look like?